So in this session, we'll be discussing different decoding strategies and see how they affect the output of large language models. Okay, so like we'll see how these, what are the parameters associated with these decoding methods, how they affect the output of a large language models, right? So by experimenting with the transformers library as well. Okay. So why do we need decoding strategies in LLMs, right? So why do we need basically? So basically we know large language models will use to generate text, right? So when generating text, basically, we will predict many possible next words, each with probability, right? See, the output of LLMs is nothing but a probability distribution over the tokens. So if we don't have a proper decoding strategy, the output looks very random as well as the nonsensical, right? So there could be a possibility of repeating too many words and lack of coherence. That means it doesn't make sense at all. Okay. So for example, without decoding strategy, the output could become too much repetition, right? The cat sat on the mat, on the mat, on the mat. So it is too much repetition of the same set of words. So what could be the key takeaway? That is, why do we need a decoding strategies in the LLMs? So basically, the decoding strategies are very crucial for controlling fluency and relevance. That is, the different tasks require different strategies for optimal results. So what are the common decoding strategies? So there are different approaches. Like one type of category is the deterministic methods, another category is the stochastic methods. So in deterministic methods, there is a greedy search as well as the beam search. Whereas in the stochastic methods, you have a top K sampling as well as the top P sampling, right? So if I want to put it in a very, the definition of the greedy search, right? So in this method, we select the token with highest probability at each step, right? So because as I said, the LLM output is the probability distribution over the tokens. So in the greedy search, we simply pick the token that has highest probability. When it comes to beam search, right? So we try to keep multiple hypotheses at each step, but ultimately select the sequence with the highest overall likelihood. So what is it and what is the meaning of this one? We'll discuss through example, okay, as we go ahead. But what is the problem with the deterministic methods, right? The deterministic methods, right? They often lead to very repetitive structure in the sentence generation, and it also sounds very unnatural. Okay, so that is the problem with that one. So in order to make the sentence structure more coherent and diverse and to make sense, that is the naturalness or the coherence, right? So we should rely upon the stochastic methods. Okay, so that's what here you can see the stochastic methods, right? So they try to introduce randomness to improve the diversity, there is nothing but a variety and naturalness of the generated text. Okay, so when it comes to top K sampling, right? So we always from the LLM output distribution over the probability distribution over the tokens, right? We try to pick the top K most likely next tokens. When it comes to top P, we try to pick a smallest group of tokens whose cumulative probability exceeds P. Okay. So for example, if you look at greedy search, right? So what is a greedy search? Basically, we try to pick argmax over word distribution given the previous words up to T minus one. Okay. So for example, if you look at this example, right? After the, this is the probability distribution over three words. So dog, nice, and car, right? And given the and nice, suppose out of dog, nice, car, after the, we have to pick, as per the greedy search, nice is the highest likely token, right? Okay, here the token is nothing but in this example word itself. Okay, but once we pick the and nice, so what is the next probable word? That is a woman, right? Because given the and nice, the probability distribution is over three words: woman, house, and guy. But the what is the most likely word? That is the woman, right? So this. So we are picking the given the next highly likely tokens are nice and woman, right? But what could be the problem with the greedy approach? So basically, so it's like the problem we'll see actually through coding thing. So for example, in order to see what could be the problem with greedy decoding approach, right? So just in order to do that one, I have taken the GPT-2. So from the transformers one. So when I kind of use this sentence, right? So I'm generating max length. These are the hyperparameters, and the input ID is here. The input IDs are the tokenized version of this sentence, right? So from the input IDs, once we get input IDs, right? So we are generating 15 tokens, okay? So if you after generating this one, right, you can see this is the sentence with the greedy approach. So what you can see is basically, I enjoy working with my cute dog, but I am not sure if I will ever be able to work with my dog. And again, the same sentence is repeated, right? So that means what are the drawbacks basically? So it kind of misses high probability words hidden behind the low probability words, right? That is, the word with high probability might be missed because it is behind the word with a lower probability. So the greedy search fails to capture such a sequence. Okay, so what does it mean? Like if you want to understand this statement, right? That is missing the high probability words hidden behind the low probability ones, right? Just look at this example. Suppose here after the we are getting nice, right? Nice. But actually, if you look at after dog, see the dog is although inferior compared to zero point 0.5, but there is a has, which is if you look at this probability complete, the dog has, it is a 0.36 probability, but this branch, the nice woman, is a 0.2 probability. So we are not able to pick this branch because the dog is having a lower probability compared to nice after the, right? So that's why we are able to miss this path. Okay. So because this highest probability token is hidden under the lowest probability token compared to the nice. So that's why we are able to, we are missing in the decoding stage, right? So that's what you can see here. Uh, the dog has is a 0.36, whereas the nice woman is a 0.2. But because of the greedy approach, we kind of chose this one, right? So that's way in order to pick most probable path. So the greedy approach doesn't help. So that's where actually the beam search is the kind of technique we should rely upon. And that kind of one is the better one compared to the greedy search. So that's what here we are saying. The beam search reduces the risk of missing hidden high probability word sequences. So it keeps track of most likely numbeams hypothesis at each time step. Okay. So what is this the hyperparameter we need to keep, we should know. So numbeams means basically we are trying to keep track of uh, two most likely paths. So it suppose when we are predicting one token, right? For example, at timestamp. So we are kind of preserving the dog and the nice both. At time step two, we are kind of picking these two. The dog has and the nice woman both. So we are trying to pick two things, and out of that one, we are trying to pick most probable path. Okay, so that we will not miss the words or tokens which are high probable but hidden under the low probability, low previous low probable token, right? So the num beams is nothing but it is like you can think of two paths along the prediction things. Okay, so the main takeaway is what? So beam search can find sequences with higher probabilities than the grid search, right? Because in the greedy search, we will be missing this path completely. But in the beam search, once we have done a two token prediction, right? Based on the total cumulative probability, we are choosing the dog has. That means the greedy search will never miss them compared to greedy search. In the beam search, we'll be land up with the most probability probable sequence path. Okay. So basically, in order to achieve this one, right, beam search, so we have to choose num beams greater than one. Okay. And early stopping is also one of the hyperparameter. One should set it to true in order to use the beam search in the text generation. That is same model, that is the GPT-2. Here, what actually, along with the input IDs and the max length, now we need to specify the num beams and early stopping true. Okay. So when we run this one, right? So here So model I have to define this one. So here, because I'm using the same model, it takes a bit of time. So yeah, now it's done. Yeah, it's done. Now we have that model thing. Now it runs. Same model. So we are setting the five num beams, and that means it tracks actually these five paths kind of thing. Okay. So in order to arrive at the most probable sequence, num beams, and the early stopping is also, these two are the actually, in order to ensure, in order to use a beam search, right? These two are the hyperparameters we need to set it up in the GPT-2 or any other transformer-based large language models. Okay, but after using this also, you can see basically here you got a bit of diversity compared to greedy search. Okay, that is, the results is arguably, definitely it's a more fluent, but still repeats same word sequences, because here you can see I'll be able to walk with him again, and I'll be able to walk with him again, right? It is still, the repetition is still there. So the remedy for this one, right? So we have to introduce the n-gram penalties. So it is like n-gram is nothing but set of word sequence of n words, for example. Okay. So suppose the most common n-gram penalty ensures that no n-gram appears twice, right? Try to understand here. If we are setting n-gram penalty, that means no n-gram appears twice. That is, the setting the probability of the next word that would create previously seen n-gram is 0. Okay, to test this one, right, there is a hyperparameter in the model, that is the no repeat n-gram size. Okay, if I'm setting this 2, right, in the beam search, when we try to set n-gram penalty to 2, that means there is no two-word sequence, which is, I mean, if that happens previously, right, the probability of happening that one again is 0. Okay, when we run this one, right, so, and we'll compare with the previous one where n-gram, no repeat n-gram size was not the we didn't set in the previous setting. So you can see that a bit of, you can see it improved, right? Here there is a repetition, but you don't see that repetition over here, right? You don't see the repetition what we saw here, right? So what is the right combination is, basically we have to use beam search along with the n-gram penalties. Okay, just to make sure that it is a bit not repetitive, that is, the repetition doesn't appear anymore if you use a beam search with n-gram penalties. Okay, but nevertheless we have to be a bit careful here. That is, when we are writing a article, right, about particular city, we shouldn't use n-gram penalty, because otherwise the name of the city would only appear once in the whole text. Okay, so that is one thing. And comparing basically the top beams, right? Top beams means it's like most probable beam paths. So another important feature from the about the beam search is we can compare the top beams after generation and choose the generated beam that fits our purpose best. Okay. So how can we achieve this one in the transformers, right? So num return sequences. Okay, it should be less than the num beams. Num beams, what? It's like the paths which are most likely, right? Suppose if you num beams, I told you, right, already. So it is nothing but the number of that is number of paths that are most probable, right? But num return sequences, right? We need to choose it is lower than this one. That is, we want to choose uh, num return sequences specifies the number of sequences that we need to pick out of num beams. If we don't mention it, right, by default it's going to be 1, right? So that's where we are specifying num return sequences here 5. Okay, so num beams also 5. That means actually it is going to give 5 different variants while generating the text. Okay, that is this. Here you can see, suppose I'll run it again just to make sure that, yes. Okay, if you run it right, here you can see that it is still actually, there is no variation much. It's like There are more or less all the variants are same, right here. So yeah, from this one, right? If you see the five beam hypothesis exhibits only marginal differences, which is expected when using just five beams. Okay, so there is it's we are expecting same thing. So what could be the limitations associated with the beam search in open-ended generation? The predictability in length. So what does it mean? So basically, beam search excels in tasks with a predictable output length, okay, such as machine translation or summarization. So, but because of this one, it becomes a limitation for open-ended generation, because the open-ended generation, such as the dialogue or story generation, often has varying output lengths. Okay, and the repetitive generation, another limitation. So beam search tends to produce repetitive outputs, especially in the story generation. You can see here that. Okay. So balancing no repetition penalties, avoiding identical n-grams requires extensive fine tuning. So that's what I was mentioning. So in order to, because the n-gram penalty, right? So it's a bit of challenge to set it up because it also depends upon the task specific. Okay. Not only that, so this predictability in length and the repetitive generation, along with these two, there is a surprise factor in the human language, right? So the human language becomes, it's like basically a high quality human text, right? This one often defies predictable next word distributions. So there is an experiment presented in this paper. See, here you can see in this plot. See, we prefer generated text to be surprising rather than boring or predictable, right? So the authors basically presented this one by comparing probabilities assigned to the human text versus those generated by the beam search. You can see there is a huge randomness in the human text compared to the beam search. Beam search text is less surprising. So in order to, so although beam search shown bit of superiority over the greedy search, but still there is a that naturalness is missing as well as that diversity is also missing. So in order to improve upon it, we should introduce some randomness. So that's where the sampling methods comes. That is the stochastic methods. Okay. So if you look at basically what is the sampling method, the sampling involves randomly selecting the next word based on the conditional probability distribution. So what does it mean? So the probability of the next word given 1 to t minus 1 words. So we are going to sample out of this conditional distribution. So for example, if you look into this, right, assume that there is a nice dog car at t equals to 1, suppose, and another sampling instant, there are other distribution over the words drive is terms. Key insight, right? So the word car is sampled from, so here, suppose we are sampling the car drives. So the car is sampled from probability of word distribution given the. So what is that probability of probability distribution of words given the nice dog car, right? Similarly, the word drives is sampled from probability of word given the and car. So what is the distribution? Drive is terms, the probability distribution over these set of words. So in order to kind of put kind of introduce sampling strategy while decoding, right? We have to set do sample flag equal to true to enable sampling. Okay, and there are other things also to deactivate top k to 0. So and we have to set the random seed as well, that we can see here. This is simple sampling from the random sampling from the conditional distribution. In order to do that one, we have to set do sample equal to true. So this enables basically sampling instead of greedy decoding, and max length equals to 50. That is the max length of the generator output, and the top k equal to 0. So this basically this kind of do sampling equal to true and top k equal to 0, basically it enables using a sampling strategy instead of greedy decoding. Okay, if we run it this, right? Yeah, so you can see actually same sentence I've been using. So I enjoy working with my cute dog, she says. you get a lot of flow and eventually greedy guy comes. So it's, you can see it's a bit of more natural sounding, right? So, but what is missing? It's like too bit of random, right? It is like there is no coherency. The generated text, if you use a random sampling strategy, you will end up with sentence that lacks coherence. Okay. So this incoherence is the common issue that we face when sampling word sequences. Okay, what could be the solution to handle this one? So what we need to do is basically sharpen the distribution to improve the coherence. So that means that rather than sampling from a uniform distribution, we need to sharpen the distribution. That means we have to reduce that flatness. So it's like increasing the likelihood of high probability votes while decreasing the low probability ones. So this can be achieved by the temperature parameter in the large language models or whatever. So when we set the temperature to zero, means it is like there is no randomness, right? That means it is a highly delta distribution, right? So when set the temperature equal to one, it is kind of a uniform distribution, more randomness is going to be there. Okay, so the temperature basically controls, it's like the distribution of the probability distribution over the tokens. So if it is temperature is one, then it is uniform distribution over tokens. Otherwise, it is bit of peaky. That is a sharp distribution. If temperature equal to zero, it is kind of, you can think of it is a delta distribution. Okay. So it's like you can see with the lower temperature, the conditional next word distribution at step becomes sharper, right? This one, you can see that actually, suppose that t equal to one means this distribution, right? After the nice dark car, you can see that it is a bit of peaky, right? It's not a uniform. Nice is clearly dominating over other words, right? Similarly, this significantly reduces the chance of like selecting the less probable words. So when it becomes a sharp right, it is very highly unlikely that we are going to select the car, right? So basically we can control this distribution over words by controlling the parameter temperature. Okay, so if we do that one, right, you can see that basically now it is makes sense. There is a coherence, right? Now it's not a random sentence like earlier. So earlier it is was the national credentials, the great guy comes. It is there is no relation to the previous sentence because of the too much randomness. But now because of the temperature parameter, if you look at it, there is some kind of a coherency coming into the play in the sentence. Okay, so but when temperature scale becomes equal to greedy decoding, when temperature becomes zero, right, it is almost equals to the greedy. Okay, it suffers from the same issues as before that are associated with the greedy approach. So in order to handle that one, actually there is one more method under random sampling only, that is a top K sampling. So rather than sampling from all the words, actually now we are trying to choose K most likely next words are filtered. Okay, the probability mass is redistributed among the those K next words. Okay, so to illustrate the top K sampling, right? So we extended the word range used from sampling from 3 words to 10 words. Okay, suppose for example here, uh, focus on this one first plot, probability of the conditional distribution of the word sequence given the. So what are the things basically when we are picking 6, right? So the distribution is controlled within the 6 words only. Okay, so in the first step, 6 most likely words encompass about 2/3 of the total probability mass. So in the second step, it includes almost all of the probability mass, right? That is, if we try to fix k equal to 6, if you take those 6 words, right, the cumulative probability is almost reaches to 199. That means the not these small told. These are the words actually they doesn't carry any probability associated with them. Okay, so this approach basically it is good at eliminating less relevant words such as not the small told. Okay, because at every time we are restricting our uh, pool of words is only to top K. That said, if I'm saying it is 6 means it always we pick the top 6 highly probable tokens. So from that only we are going to sample it. So that's what we are going to do. So it's like top k, suppose here I'm setting 50 and do sample. That means first we restrict, we try to pick 50 words which are highly probable next tokens, and from that one we are going to sample it. Okay, that okay. Now we are going to randomly sample, but we are not going to randomly sample out of all the words, but we are restricting our sampling sequence to 50 words. Okay. So this kind of basically introduces a bit more coherency, like human sounding text. So if we do top k and then do sample, suppose if you ignore top k to zero, right? It's like there could be a probability that you can pick very less relevant words when you are randomly sampling. So you are avoiding that one by picking top k 50, and out of that one you are doing a random sampling. Okay. So this improves human sounding text. Okay. But what could be the concerns with the top k sampling? Okay. So as I told, because if you look at it, right, this is bit of flat compared to the second, right? Probability of W given D is bit of flat compared to probability of W given D and car. So it is bit of peaky, right, in the distribution sense. So what happens is some words are sampled from sharp distribution, other words are sampled from the flatter distribution. So it does not dynamically adapt the number of words filtered from the next word probability distribution, right? So there could be a probability that top k eliminates the reasonable candidates, right? So in step two, it it includes ill-fitted words like down A in the sample pool. Okay, because it is trying to eliminate some of the reasonable words, and it is trying to include down and A which may not be relevant. So it doesn't have that much control. So that means what could be the implications with the top k with the random sampling? So basically, it produces gibberish for sharp distributions and limits the model creativity for flat distributions. Okay. So in order to handle the problems associated with the top k sampling, so another technique is top p sampling. So instead of sampling word only from most likely keywords, so top p sampling chooses from the smallest possible set of words whose cumulative probability exceeds from the probability p. That means basically, rather than sampling from top k words, so we try to sample from the words whose cumulative probability is greater than or equal to the chosen probability p. For example, if we are picking p equal to 0.92, right, then the top, basically in this one, right, you can see there are 9 words whose cumulative probability is 0.94. But when it comes to second one, it is 3 words. Now we are trying to throw down unnecessary words like down and a kind of things. Okay. So this maintains wide range of words when the next word is unpredictable. This is interesting, right? Suppose when the next word is unpredictable, so it maintains wide range of tokens. But when the next word is predictable, it tries to achieve very peaky distribution. Okay, the hyperparameter here is you need to set a top k sampling. Okay, so that is basically here top k is 0. That means we are not picking the number of words. Okay, so we are setting top p equal to 0.92. That means we have to pick the tokens whose cumulative probability distribution is greater than or equal to 0.92, and out of that only we have to sample the next token. So because of that one, so it's like if you see it, right, it is not too much gibberish. Okay, but it is bit of, I still see some kind of a randomness. It's like, see, national credentials is still coming. Okay, so the generated text is, they say it is resembling human writing, but it's not perfect yet. So what they suggested is we have to use a combined technique, top P and top K samplings together. Okay, so what they have done is basically we have to set and top P 0.95. Okay, so and that means we are applying both together. Means we want to pick top 50 words whose cumulative sum is greater than 0.95, and out of that only we have to do random sampling. Okay, so and the number of return sequence also we are giving 3. Okay, so when we run it, right, We'll see how the sentence structure is going to be. Now you can see basically it's like three sentences as we saw with the beam search, right? There is a lot of overlap, not marginal difference only. But if you see here, when we introduce top P sampling along with the top K, so then this combination is trying to introduce bit of diversity across the sentences, right? So that is, but overall, right, the top P and top K samplings are effective ad hoc decoding methods. Okay, in a conclusion, right, the top P and top K together provides a better performance than the deterministic approach, such as a beam search and greedy search. Okay, but as I told, so here whether it is a top P, top K, beam search and greedy decoding. So we cannot say which one is like it is a task specific. If we have to experiment with it, one size doesn't fit for all the tasks. Okay, so based on the specific use cases, we have to experiment with it. But overall, we can say on an abstract level, top P and top K is working better in this case. Okay, but concept wise also top P and top K introduces a bit of randomness and the coherency. So that's where, and the diversity. So that's what we have observed over here, right? So that is the conclusion. So there are what we discussed basically greedy search, beam search, and the top K sampling and top P sampling. And what are the hyperparameters we should play with in order to bring in these strategies into the decoding approaches. Okay. So I think this is a very short and quick review of different decoding methods used in the LLMs. Thank you.